Let us solve a circuit in using Laplace transform, and this lecture is, what is the number of this lecture? I think it's 12.4. So let us take an example, and this example is a little involved, not a simple one, although we should be starting with a simple circuit in order to understand the Laplace transform. But today I'm choosing to start with a circuit that is not the very simple one. I hope that in doing this, we are going to learn several things that may come into problems posed in the assessments or exams, and you may therefore be able to understand how you are going to handle such a situation. I still adhere to what I used to say, that in order to learn something, we need to begin doing things on very simple problems. So, this is what I expect of you. Although you are going to learn from what I am going to do, but once you uh, have gone through this lecture, take very simple circuits yourself and try solving them. So, for example, let us say we are presented with a circuit and we have a capacitor here, a resistor here, and an inductor here with another source in this loop. So suppose this source is 4 ut, the unit step function. This inductance is of 4 henries, 0.5 farad, and 1 ohm. And we have 2 plus 5 ut written here. And this is very important to see that this ut only multiplies 5, not 2 volts. The question includes, this is a reference node, and that this is Vx. So the question says find Vx using node, what is the exact, okay, using nodal analysis technique. This is basically book example 15.4 from the Heights book. And we can clearly see that we can solve this question using whatever we know, um, using the knowledge of LCA, where we studied how DC sources can be applied and responses can be found for series RLC and parallel RLC. It would be a good exercise if you can do this using those concepts. However, please note that if you want to try that, um, these two sources should be taken separately and then using superposition basically to solve for the requirement. So basically you are going to short this, take this source and find this Vx, say it is Vx dash, and then short this and take this source and find this Vx double dash, then Vx would be equal to Vx dash plus Vx double dash. However, today we need to learn how to solve a circuit using Laplace transform, and be cautious. The way I am going to do right now, without telling much how we are going to actually treat circuits using Laplace transform, this would be a little longer method. The good news is when we want to do it in actuality, once we have learned this topic of Laplace transform and how circuits are solved using it, we will see how it can be done in a simpler way. So before I begin, there are several things you should remember. One, that Laplace transform of a function f of t is defined as solving this integral from 0 to infinity, where the function is multiplied by e raised power minus st with respect to time. So the t gets eliminated and all the function that we get is in s. So it is an integral from 0. So anything happening before 0 uh, cannot be handled using Laplace transform. Now this is a source. If I have to draw it, just in order to understand how things really are, against time, this source is basically what this line is telling. It is 0 before 0 and it is 4 after t is equal to 0. And what about this one? So if we want to plot this against time, it is saying that this ut is not multiplying 2. So it has always been 2 when 5 ut gets added to it. So it is 2 before t is equal to 0 and then 5 afterwards. So you should pay 5 afterwards, and since 5 gets added to 2, basically it becomes 7. So if we have to mark the scale, then this is 0, this is 2, this is 7. 5, a step of 5 size is added at this point. This is very important. So you see this 2 is what is before t is equal to 0. And for a time before 0, we cannot use Laplace transform to solve it. But let's draw the circuit. So before t is equal to 0, we have a source here which is 2 volts, a capacitor, same capacitor, the inductor, and no source here because it is 0. So how can the voltage across this source be 0? By short circuiting it. So this is replaced by a short circuit and we get this situation here. So what we are interested in are the initial conditions, since when a circuit have energy storing elements, capacitors and inductors, we always are interested to know what are their state, energy state, when our interest started at t is equal to 0. So when this circuit was at t is equal to 0, what was the voltage across the capacitors, so this capacitor, and what was the current through this capacitor, and we are going to find this using this period. So because this time is what established the initial energy in the circuit. So let us say this is the voltage we are interested in finding. Let us call this VC. So remember, we have to mark this VC over here. It's not in the question, we are marking it ourselves, but we should always refer this to it. So this is for a period t less than 0. But if and similarly, we are also interested in this current. So let us mark it, say IL, and the same current IL over here. So let us draw the circuit exactly at t is equal to 0 minus just before 0. So what is going to happen? We have a source 2 volts still there, 5 has not kicked in yet, and because this is a DC source, what I am going to do now is purely only to be done for DC sources. So we have a DC source here. So the capacitor would have charged by now and it has been replaced by an open circuit. A resistor remains there and a inductor would have been replaced by a short circuit. So inductor replaced by short circuit. If a DC circuit has inductors and capacitors for a long time, so how long had this 2 been applied? Since eternity. from minus infinity to 0 it was there, so this was replaced by an open circuit, and this VC at 0 minus is what we are interested to find, and this IL at 0 minus is what we are interested to find. So what is going to happen? This resistor is shorted out by this. So both ends of the resistor are joined together. So no current is going to pass through this resistor. Current in any way cannot pass it through it because the voltage source has been opened up because of the capacitor. So basically, what will be the value of IL 0 minus? 0. And what will be the value of VC at 0 minus? So if this in this open loop or this one, whatever loop there is, we can apply KVL. So minus 2 plus VC is equal to 0. So VC 0 minus is 2 volts. This voltage appears across the terminal just like across the battery. So you see this is at the positive terminal, this side is the negative terminal, so 2 volts appear there. This is going to become what we are going to say about the initial conditions for the differential equation or the integral differential equation that we are going to work with, and should be super clear because of the how they behave, that the current through an inductor does not suddenly change. So when this 5 ut has kicked in and this 4 ut has kicked in into the circuit, the current through the inductor at that time just after 0 would still be 0, and the voltage across the capacitor would still be 2 volts. It will not suddenly change. However, we are not concerned with VC, we are not concerned with IL, we are concerned with Vx. So what would Vx be here at that time is what we are going to be interested in. So let us spend it to when we are ready to handle that. Okay, so now we have initial conditions. Very important step, and very few people would be able to notice once the theory has been taught and such a circuit is presented. So they will not know how to handle this too. So that's very important. This 2 was there to establish the initial conditions. For understanding sake, now let me draw what the circuit is going to be at t equal to 0 plus, just after 0. So now the circuit would be, we have a voltage source of 7 volts, a capacitor, a resistor, an inductor, and a voltage source of 4 volts. So we can now say it is 7 ut and 4 ut, just to remind us that in Laplace transform tables, if the what basically transform pair is to be looked at. So we must know that the Laplace transform of ut is 1 over s. So that of 4 ut would be 4 over s, and 7 ut would be 7 over s, and so on. But we will come to that later on. So this is the circuit that we are interested in, except that now we know that there is an initial voltage across this one and no initial current here though. So we are clearly marking the voltage and current so that there is no ambiguity. Now let us come to the solution. So in time domain, what we would do is we will write the node voltage equation. So let us write the node voltage equation here for this case. Let us try to conserve our space. So write the node voltage here. So this outward current, this outward current, this outward current. So what we are going to write is the outward current through a capacitor. By definition, if you remember the formulas, IC is equal to C dV by dt, and VL is equal to L DIL by dt, and you know VR is equal to IR into R, and the other formulas that involve the integral. So VC is equal to 1 over C integral minus infinity to T of IC dt, and IL would be 1 over L integral minus infinity to T VL dt, and IR is equal to VR over R. You already know that. So in writing this outward current, the voltage across the capacitor is Vx minus 7. This is 0, 7 volts. The Vx minus 7 is the voltage across the capacitor. So we are going to write Vx minus 7, the derivative of this thing, into C, which is 0.5 farad, plus this outward current, which is Vx over 1, plus, now this outward current would be Vx minus 4, and integral from minus infinity to T of 1 over 4 dt is equal to 0. So this is the NVA equation for this circuit. We can differentiate throughout to get a second order differential equation, or we can keep it like this, doesn't matter. Now we have to look up the tables where we can see in the functional transform table that a derivative of a function has a Laplace transform of s into the Laplace transform of the function minus the initial value of the function at t equal to 0 minus. And the other thing is the integral of a function as a Laplace transform of f of s over s. You should remember some of the functional transforms as well as the transform pairs. That will come in handy. However, in any case, the tables are given, so you don't need to cram anything. So basically, making use of these, we can very easily see. Let us take the Laplace transform throughout. So what do we get? 0.5. The Laplace transform of Vx minus 7. This 7 is actually 7 ut. Do not forget that. Let me write it explicitly. And we can write 0.5. This is the derivative of a function. So we get s times the Laplace transform of the function. So Vx is Vx of s actually, but I am skipping that, minus the Laplace transform of 7 ut, which is 7 over s, minus, now Vx minus 7 is in the opposite polarity of this Vc. So what is the initial value of this thing? It is minus 2. So minus is from the formula, and this minus 2 is from the value. So this is what we get here, plus what is the Laplace transform of Vx, capital Vx, plus what is the Laplace transform of the integral of this thing. It is simply capital Vx minus 4 by s over s from this. So you should be able to extend and expand a result taken from the table onto what you are actually doing. Be very careful. So what do we get? We got 0.5 s. So be very careful with s and 5. In hurry, 5 can be confused as s and s can be confused as 5. So you can change things if you are not really cautious. So s multiplied by this s is going to cancel, and 2 into 0.5 is plus 1 plus Vx, and we are going to have plus Vx over 4s minus 4 cancels with 4, 1 over s square is equal to 0. So probably it would be easier for us, it may be, may not be, but we can multiply throughout by 4s square. So let us keep it outside because at some stage we have to factor it, and we get, and let us take this common as well, Vx common. So we get 0.5. Actually, we should bring this 4 in. No, I think we cannot take this, keep this outside because we have to cancel this part. So it comes in, it becomes 2s cube minus 4, 3, 12, 14 s square minus, this is minus 2.5 actually, 2.5 into 4 is 10. No, I am doing it incorrectly because this does not have a Vx in it. So this is a separate term. So let us factor Vx out later on. So we are going to get 4s square Vx plus s Vx minus 4 is equal to 0. So this bracket is for no use here. Now we can write Vx taken common 2s cube plus 4s square plus s, and the constants can go to the other side. So we have, or not the constants but the terms that do not have Vx in them, 10s square plus 4. So we got Vx is equal to 10s square plus 4 over s common 2s square. This 2 can be brought out, so we can have this 2 from here as well. So we are going to get 5 square plus 2, so that these cancel out. So we got s square plus 2s plus 1, and we can factor this to be, what will be the factor here? It's s plus 1 whole square. 5s square plus 2 over s into s plus 1 whole square. I think I may have committed a mistake when we take 2 common outside. This will become 0.5. Okay, so why we have taken that outside? We shouldn't have. Okay, bring it back. Or now if we have taken it, let us write this 0.5 now. So this is actually not this case. It is not a perfect square. S square plus 2s plus 0.5 equal to 0 can be factored using the quadratic formula. So we are going to get minus b plus minus square root of 4 minus 4ac, which is 2 over 2. So we get minus 1 plus minus square root 2 over 2, which is going to be minus 1 plus minus 0.707. Is that right? It will be 1 over under root 2. Under root 2 is 1.414 over 2. Okay, right. So instead of this, the actual term becomes 5s square plus 2 over s into s, one of the factors that goes on the other side, s plus 1 plus 0.707 and s plus 1 minus 0.707, or 5s square plus 2 over s into s plus 1.707 and s plus, what do we get here, 0.293, maybe 0.293. And now we need partial fractions expansion to see that this term would actually be equal to, I'm not writing this term here, in fact I should write by, or maybe we can refer to it from there. It is going to be equal to a over s plus b over s plus 1.707 plus c over s plus 0.293. So what would a be? What we have to do is multiply throughout by s and then put s is equal to 0. So we are going to get 0, 2 over this term, in fact, this term, 0, 0 and only 0.5. So 2 over 0.5. So a would be 4 and b would be multiplying throughout with this term and then putting s is equal to minus 1.707. So we are going to get 5 into minus 1.707 square plus 2 over s, which is minus 1.707 into minus 1.707 plus 0.293. Let me use the calculator on the laptop. So we get 1.707 minus 0.293. This is 1.414. 1.414 into 1.707 would be 2.414. 2.414 would be actually positive, because this is negative, this is negative, this is positive. Control C this, and we are going to get 1.707 square multiplied by 5 plus 2 divided by, I think the answer is 6.865. I hope I have not committed any mistake. So similarly, C would be equal to 5 minus 0.293 square plus 2 over minus 0.293 into minus 0.293 plus 1.707. So we are going to get, let me do it. So 1.707 minus 0.293, 1.414 into 0.293, and this time it would be negative 0.414, and we get 0.293 into 0.293 into 5 plus 2 divided by, is 5.863. So now, since we are almost near the end, I don't want to flip the page because I want to hide the result here. So you understand what is A. So now if you look at the table once again, A over S would be Laplace transform of AUT. AUT would have A over S. So what's the value of A? So the answer would be Vx would be equal to, that we want to find, equal to 4 ut. So basically we are going to write that ut with all the terms at the end, and this b would be plus 6.865, and again in the transform table you can see 1 over s plus a. 1 over s plus a is the Laplace transform of e raised to the power minus at ut. So b over s plus something would be Laplace transform of b e raised power minus 1.707t. So this is b e raised power minus 1.707t plus 5.863 e raised power minus 0.293 t ut should be the Vx that we are looking at. I think I have omitted this fact that this would be negative. So actually this would be negative here, and we are going to get a negative sign here. Let us verify. Let us check if the answer is correct. So how would we check this? So let us put t is equal to 0 here. So what do we get? 1, 1. So we get Vx at 0 plus would be 4 plus 6.865 minus 5.863, which is 4 plus 6.865 minus 5.863, which is 5 volts. Now let us see if this is indeed the case. So just after 0, this Vx is 5 volts. Let us verify this. So this is 7 volts. This is 2 volts, right? So this is 0. This point is at 7. We have a drop of 2, so we get at 5 volts. I hope you understood this. We have 7 volt here, or we can have a have KVL applied. So minus 7 plus 2 plus Vx is equal to 0, which gives us Vx is equal to 5 volt. So it is verified, at least by checking this condition, that this is true. So while much of the labor in using this partial fraction expansion would more or less be the same, but there is a shorter way of omitting writing this integral differential equation in the first place. There is a way it's possible that we can directly write an algebraic equation, and that we are going to learn in the next video.